In this video, we'll be presenting kinematic problems. They will be about not finding the shortest path, but the fastest. Here's the first problem. Consider point A to be on the sand and point B to be on a road, where you can run twice as fast. What's the fastest way to go from A to B? You need to calculate x over d. And here's a hint. X over d is a number between 0 and 1 that says at which point between 0 and d you need to hit the road to get there the sooner. Now this is a piece of cake, certified. On one hand, you need to reduce your time in the sand. On the other, it makes your path longer. This seems to be another one of those maximum and minimum calculus problems. Yeah. Let's see. Say Vs is the speed on the sand and Vr the one on the road. Then the expression for the total time is, well, time on the sand plus the time on the road. The time on the sand being the distance from A to x divided by the speed of the sand, and the time on the road being the distance from x to b divided by the speed on the road. All we need to do is find the value for x that makes the derivative of the time from A to b equal to 0, right? Let's see, where were we? Finding the value of x that makes the derivative equals to 0. So that piece of cake here. That's the derivative. I hope you still remember how to do derivatives, right? Okay, let's get rid of the radicals and put them in terms of x over d, which is what's being asked, and Vr over Vs, which is 2. There. Are you already terrified, or should I go on? Oh my God. This is a 4th degree equation on x over d. Wow, you're in deep, you know what. But don't panic. Fortunately, you live in the 21st century. And Excel can come to the rescue. Let's go back to your equation for the time from A to B. Yeah. We don't really know the values for D, Ds, or Vr. All we know is that Vr over Vs is 2, and that the answer we need is x over d. So let's multiply Vr over d to get the expression in terms of what we know and what we need to know. There. Let's focus on this left-hand side of the equation and rearrange it so as to get the time over the quotient of the d over Vr, which is the minimum time for getting out of the road from point B. Let's call this ratio R and replace it in the left-hand side. So R expresses the time from A to B in units of the time from B to the road. Is that cool or what? All we need to do is use Excel to calculate R for every value of x over d at say 0.1 intervals between 0 and 1, and look for the value of x over d for which R is minimum. That's a piece of cake then. Let's go and open an Excel worksheet. Let's start with the headers. X over d on column A and R on column B. Now enter 0 for the first value of x over d, and 0.01, the interval, as the second. Select these two and run it down. Now we need to enter the expression for r, that one. Translate it now into Excel commands. Insert the sentence in the first cell under r and run it all the way down. Now go through the list looking for the minimum value of r. There it is. And here's the solution to the problem that at some point seemed out of reach, right? Once you master Excel, you can get as fancy as you want. But let's get just a little bit fancy here. Let's put the data in the columns into a chart. The minimum shows beautifully. But what if VR over VS was 1 and not 2? Go to the expression in the first cell, change the 2 for a 1, and run it down. Now the minimum has go to the middle. Can you explain why? And here's problem number 2. Imagine a project for a skating mini ramp. The perfect profile would be that in which the skater goes from a higher point A to a lower point B in the shortest time. What should be the shape of such a profile? Maybe a straight line from A to B, or something like this, or even like this. The answer should be a blueprint of the profile, a template, something that can be drawn in a piece of paper to help guiding a jigsaw. Could it be a parabola segment? Maybe it's a hyperbolic or exponential. What about an arc of a circumference? This problem is way older than skateboards. It is the famous problem of the Brachistochrone, from the Greek brachisto, shortest, and chrone, time. It goes back to Galileo in early 1600s that suggested it was an arc. He was smart enough to discard a straight line, but very clever minds at the end of the century proved that it was not an arc. In 1696, Johann Bernoulli challenged the great mathematicians of his time with this problem that he published in Acta Eruditorum, the first ever scientific journal. Beside his own solution that was corrected by his brother Jacob, fact Johann tried to conceal, another 4 were submitted. Newton learned about the challenge in 1697, directly in a letter from Johann Bernoulli. Though he disliked being challenged by lesser foreigners, he solved it overnight with an approach that began a whole new branch of mathematics called the calculus of variations. Gottfried Wilhelm von Leibnitz. He developed the differential integral calculus independently from Newton, and also submitted his solution to the Brachistochrone. Remember that theorem that saved the day when trying to figure out thought problems and limits? That was Guillaume François Antoine Marquis de la Hôpital. He submitted his solution to. Finally, I'm going to attempt to pronounce his name. Ermfried Walter von Triumphhaus. He also submitted his solution. He was a great mathematician and philosopher, but his unpronounceable name has transcended mostly for invented porcelain in Europe. No one ever knows if and why he's going to transcend, right? No computers and numerical methods were available then. And it is what's going to allow us, less brainy creatures of the 21st century, to take the challenge. Remember this expression that took us nowhere back in the first problem? This one, we can rearrange it like this, and like this. And look at the distance traveled on the sand, the decomplement to x, and the distance traveled on the road. These two expressions are the sine of these two angles, theta 1 and theta 2. But wait, this is Snell's law from optics. What's it doing here? And yes, this is a Snell's law. Our original equation came from an attempt to find the minimum time to go from A to B. But according to Fermat's principle, the path of light is always that of the minimum time, hence the same result. Speed will increase as the skater descends, calling y what it has descended. Then, the kinetic energy will be equal to the change of the gravitational potential energy. Or, isolating v, it equals the square root of 2gy. I'm sure you've seen that before. A ramp can be imagined as the set of infinite layers with different speeds that increase with the square root of y. If the skater was light, what would be the path? Let's forget about B for the time being and consider A as the point where the movement begins, with V equals 0. To apply numerical methods, the speed continuum must be discretized. The sign at level n can be expressed in terms of its speed and the date of a contiguous level. But since the speed equals the square root of 2gy, the sign may rather be expressed in terms of the amount descended. What will be the depth of the ramp, y sub n? The sign at the lowest level, say uppercase n, must be 1, its maximum value. And so, the sign at the level before that one must be the square root of the quotient of y over the maximum depth of the ramp. Now, we can recurrently work our way from there to point A, where y sub n will be equal to 0. What about x? The value of x at level n is that of the previous level plus the increment of x, which is the increment of y multiplied by the tangent of theta. Replace now the tangent for the sine over the cosine. And since we have all the values of the sines, it is convenient to express it in terms of the sines only. We can start evaluating for n equals 0 and work our way to the last n. Actually, the one before the last, to avoid dividing by 0 when the sine of theta equals 1. Time for Excel. Yes! The number of speed levels will depend on the accuracy required. As always, since it has not been specified, let's pick an arbitrary one, say n equal 200. So as we have done before, open the worksheet and enter the headers. Enter 0 and -1 as the first two values for y. We don't want the chart to show upside down, do we? Run it down to -200. Enter the last value for the sine of theta, which is 1. On cell 201, enter the recurrent expression for the sines. Here's a translation to Excel. And run it all the way to 0. In cell B2, enter 0 as the first value for x, and in B3, the recurrent expression for the x's. And run it down. Oops, Not so far. Back one. Okay, we're ready to plot a chart. So select the columns with the x's and the y's and insert a scatter chart. And here it is. It's just half, and there's 1 point missing. Let's get back to that missing point and allow the divide by 0 to happen again. To avoid it, we can take the previous sign value instead of 1, which was what sent x to infinity, right? Keeping the same angle will make the roller land a smaller x, but the real thing must be nearby. Too far wouldn't make it the fastest, would it? Repeating this, but with 2,000 instead of 200 points, now the x must come closer to the mystery value. Again with 20,000 this time. 200,000 now. Is this 314 ringing any bells? The missing value of x is not other than pi. Let's plot the other half of the chart by running down the y from 200 back to 0. Now on cell 202, we enter the expression for the sign that is recurrent to the previous cell, not to the next cell before. And we run it down until it's back to 0. Now the x. If the missing point at the middle was 100 pi, then the last value of x must be 200 pi. Finally, in cell 401, we must enter the Excel translation for the recurrent expression for x. And we run with that. Finally, let's fill the empty cell. By now, the chart should be complete. Let's see how it's doing. It's there. We're still one hurdle ahead. The scales of x and y are not the same. Let's start by making the major units of the x-axis equal to 50, the same as the y. Now we need the 50 by 50 to be a square. One way of doing this is to draw a square and then stretch the chart until it fits. Like that. And that's the Brachistochrone. Where are the points A and B? Let's bring them in. Now we adjust the scale until B sits on the ramp. There. How about some gravity? But there's something those great mathematicians back in the 1600s figured out that we haven't. That curve that we found numerically is a cycloid. You may Google the Brachistochrone to find those solutions. There are plenty of videos and papers available. This cycloid piece of knowledge allows for an easier way to mark the cut. Check this out. Is this cool or what? And this is all for now. I hope you've learned a thing or two with this video. So long.